Welcome back everybody to another video lecture from Ms. Semino. Today we're going to be talking about percent composition and chemical formulas. So the objectives for today's lesson is to describe how to calculate the percent by mass of an element in a compound. So we're going to calculate the percent composition. We also want to know how to interpret and determine an empirical formula. And then we're going to distinguish between an empirical formula and a molecular formula. So those are the big ideas for today. So calculating the percent composition of a compound is one of the more simple formulas that we're going to have for chemistry. So like all percent problems, you're going to take two masses, multiply it by 100, and you're going to come up with a percent. So the first step is to find the mass of each of the components, okay, or the elements, and then divide by the total mass and then multiply by 100. So let's see how this works on the next slide. So the problem reads, calculate the percent composition of a compound that is made of 29 grams of silver with 4.3 grams of sulfur. So remember what we said, you're going to take the mass of each compound or substance, and in this case we've got 29 grams of silver. We're going to divide it by the total, and you're like, well, where did this 33.3 come from? So you just take this value, 29, plus 4.3, and that gives us 33.3 grams, so there's our total. Multiply it by 100, and for our silver sulfide, we have 87.1% silver. Then you just simply take the mass of the sulfur, divide it by the total, multiply it by 100, and we come up with 12.9% sulfur. So, and then notice that these two totals are going to equal 100, so that's an easy way to double check. So just a quick review. Take the mass of each substance, divide it by the total, multiply it by 100, and it'll give you the percent composition. Now the last problem was pretty straightforward. It gave you the mass of each substance. Sometimes though you're going to see the problems will ask you to find the percent composition from the formula. So what you need to do is you need to assume that you have 1 mole of the substance. Then you already know the mass of the elements and the whole compound. And these are the values that come from the periodic table. So remember how we calculated the molar mass and we looked up the atomic mass? We're going to be using those. Our first example problem here says calculate the percent composition of C2H4. So basically we need to find the percent composition of carbon as well as hydrogen. So let's go ahead and do that. So I'm going to take carbon, and there are 2 carbons, and we know the mass of carbon is 12, so 2 times 12 is 24. Then I have hydrogen, and I've got 4 hydrogens, and the mass of each hydrogen is 1, so that's 4. And then when we total this up, we know that the molar mass is 28 grams. So remember, we're assuming that we have 1 gram of this. So the way we're going to find the percent composition of carbon is we're going to take the 24 grams of carbon, we're going to divide it by 28 grams of the total substance there. We're going to multiply that by 100, and we're going to come out with the percent value. And we come out with a calculated value of 85.7%. But notice that we're only using 2 sig figs, so our answer here is going to be 86% for carbon. Then we need to do the same thing for hydrogen. So again, we have 4 hydrogen. The mass for hydrogen was 4, divided by 28. I'm hoping you guys can see this at the bottom. Multiply that by 100. And the calculator said it came out to be 14.2%. Again, we want to go ahead and round that to 14% for hydrogen. And now we know the percent composition of each element in C2H4. It's 86% for carbon, 14% for hydrogen. So you can see here, here's our problem, calculate the percent composition of C2H4, and we did that, and notice they did use 3 sig figs here, but we're only going to be using 2. So here's another problem that I want you to try out, and it says, how about for aluminum carbonate? Remember, aluminum has a 3+ charge. Carbonate's CO3, and it has a 2- charge, so you need to balance that out for the chemical formula, and then go ahead and double check your percents here. So we can also use this percent as a conversion factor. So here on this slide, we're going to talk about the difference between an empirical formula and a molecular formula. So the empirical formula is the lowest whole number ratio of atoms in a compound, and that's different from a molecular formula because this is the true number of atoms of each element that are in the formula. So let's go ahead and look at this example here. So the molecular formula for benzene is C6H6, and then if we take our C6H6 and we divide each of these by 6, our empirical formula now for benzene is going to be C1, and there's these imaginary ones, remember, H1. And so this would be CH would be our empirical formula. Another example that I like to use is for glucose. Glucose has a molecular formula of C6H12O6. However, if we take each subscript and divide it by 6, we end up with an empirical formula for glucose of CH2O. One cool thing to know is that formulas for ionic compounds are always already in the empirical formula. They're already in the lowest whole number ratio. So for example, we've got sodium chloride, so this is 1 to 1. Magnesium chloride is 1 to 2. Aluminum sulfate is 2 to 3. And then potassium carbonate is 2 to 1 as well. Remember, potassium has a 1 plus charge, so you need 2 of them to cancel out the 2 negative charges in our carbonate ion. So another thing to know is that formulas for molecular compounds might be the empirical formula, but sometimes it might not be. So for example, here's water. You can't reduce water any further because it's a 2 to 1 ratio. You can't, take 1 and divide it by itself. It won't be a whole number anymore. And so this is our molecular formula is our empirical formula. Here is our example of glucose again, our C6H12O6. The 6 is kind of down here. We said it would simplify out to CH2O. And then over here we have C12, H22, and O11. This 11 should be over here. And we can't reduce this anymore because you can't do like 11 and then 12 by 11 and come out with a whole number here. So this is already the empirical formula. So one of the tasks that you're going to be asked to do is to calculate the empirical formula. So sometimes it's easy for you to look at something and just, know it already. So here's this formula for glucose. Again, we can reduce it. Here we have CH4N, and this is already in the lowest ratio. What you also want to know, though, is that a formula is not just a ratio of atoms, it's also the ratio of moles. So this is why this is in that moles chapter. We're going to use moles to do some conversions. So in 1 mole of carbon dioxide, there is 1 mole of carbon and 2 moles of oxygen. 1 mole of carbon, 2 moles of oxygen. In 1 molecule of carbon dioxide, there is 1 atom of carbon and 2 atoms of oxygen. So we're looking at the same chemical formula, but it can mean 2 separate things. We can talk about moles or we can talk about individual atoms. So this is a little bit more complicated calculation. What we can do to find the empirical formula is we can calculate the ratio from the percent composition. And the way that you would do that is that you have to assume that you have a 100-gram sample, and then the percentage becomes grams. So if you knew that you had a 75.1% of a substance, you could just simply convert that into 75.1 grams, because if you have 100 grams, are you guys seeing how that's matching up there? So you just want to convert then those grams to moles and then find the lowest whole number ratio by dividing each of the moles by the smallest value. And I'll show you how that's going to work on the next slide. So our problem has a compound composed of 38.67% carbon, 16.22% hydrogen, and 45.11% of nitrogen. So in order to determine the empirical formula of this compound, we're going to have to assume we have a 100-gram sample. So remember what we said on the last slide. We're going to take this percent and immediately convert it into grams. So we say that we've got 38.67 grams of carbon. Then we need to convert that into moles. And this actually should be scooted underneath here to 12.0 grams of carbon. So we're converting the grams to moles. And then we come up with moles of carbon. We're going to do that same thing with hydrogen. And again, this value should be shoved underneath here. And what you're going to see is we take our percent of 16.22, we make it into grams, we then convert that grams into moles, and we come up with moles of hydrogen. We can also do that with nitrogen, convert it into moles, and have moles of nitrogen. So what you notice is we have a value of 3.22, 16.22, and 3.22 again. So what you want to do is you want to divide each value by the smallest value. So if I was to do this, 3.22, this equals 1. Of course, 3.22, This is going to equal 1, and then we can also do this with this value here. And this came out with a value that is like 5.03, but that's close enough to 5. So what we're going to find is that our empirical formula for this substance is going to be C1H5N1. And remember, we don't include the ones when we're writing the formula, so it's just going to be CH5N, and that's our empirical formula for the substance. Here's another example that you can try on your own time. It says a compound is 43.6% phosphorus and 56.3% oxygen. What is the empirical formula? Here it is right here. Go ahead and double check it. Then it also tells you that caffeine has this much carbon, hydrogen, and nitrogen, and oxygen, so determine the empirical formula there, and then go ahead and double check your answer. Hope this helps. Bye.